Okay, we're going to be reviewing for the third test, which is over chapter 3, and the third test has 18 problems on it. So I went into the homework of my math lab and searched for 18 similar problems. You can also look at this chapter 3 review over here on the side, but it'd probably be easier just to look at problems in the homework that are just similar to the ones on the test. So chapter 3 has 5 sections, 3.1 through 3.5. We'll start with 3.1. The first question is like the question 2 in 3.1. 3.1, the second question. Okay, so it says, choose the graph that represents this function, f of x equals x minus 2 squared minus 6. So this is kind of a continuation of chapter 2 with all the transformations, except we're specifically looking at a quadratic function, x squared. And this is just like chapter 2, how when I see a number that's outside of the parenthesis, it's not with x. The x minus 2, that's with x, and the minus 6 is not with x. So for me, ones with x, you do the opposite of what they look like. The ones not with x are just like they look. If it's with x, it affects the x direction. If it's not with x, it affects the y direction. So I'm going to do the opposite of the x minus 2 and do plus 2. Plus 2 would be to the right 2. It looks like you should go to the left 2, but instead you go to the right 2. The minus 6 is not with x. That one's done like it looks, minus 6, and it's affecting y, and that you do it like it looks, so it's down 6. And for a parabola, a quadratic is a parabola of the graph, for it to be upside down, you would need a little negative in front of this x here, and we don't have that. So we can eliminate choice A, because that one's upside down. Choice B, C, and D are all right side up, so it's just a matter of where the vertex is, that point at the very bottom of the parabola. And in this case, it would be at positive 2 and negative 6. We'd go 2 to the right and up 6. And this graph's going by 2s, or maybe even 4s. But clearly the answer is C, because it's the only one that goes right and up. The other one is left and down, or right and down. No, I said that wrong. So it's 2 to the right and down 6, so that's B. 2 to the right and down 6. That's choice B. This one's 2 to the right and up 6, and this one's to the left, which is wrong. And then we can check it to make sure it's right. Yep, so you're picking a graph out of a multiple choice. Quadratic graphs are parabolas. The number with x, you do the opposite of that. The one not with x, you do it just like it looks. That's like problem 1 on the test. Problem 2 is the third problem in section 3.1. We want to graph the quadratic function x minus 4 squared. So it says click to enlarge the graph. There's 2 parabola tools. You want the one that shows an upward parabola, not a sideways one. So this one's the vertical parabola tool. And then you come over and you click where the vertex would be, that starting point of the parabola. Since the function is x minus 4 in parentheses squared, the minus 4 is with x, so that affects the left and right direction. You do the opposite of what it looks like, so you go to the right 4 instead of the left 4. There's no plus or minus number that's outside of the parentheses, not with x, so that therefore it doesn't go up or down. The vertex is exactly right there. So you click the vertex. Even up at the top, it tells you that that point is 4, 0. Then, as long as you don't have a number in front of the x that multiplies or divides it by something, then parabolas, you just go right 1 and up 1, and that's how wide the parabola would be. Or you can go left 1 and up 1. Either you just do one or the other, click that spot, and then it draws it. Click the save button to save it, and then you can check it. That's part A, is graphing it. Or actually, that's just doing, you have to graph it first before you get to part A. Now, the vertex is the coordinate 4, 0, because the parabola goes right through 4, 0. The axis of symmetry is an imaginary line that would go vertically right down the middle of the parabola. So it's a vertical line right through the x value of 4. And that's why the equation is called x equals. It goes right through the x-axis of 4. So the axis of symmetry is x equals 4. The number of it is always the exact same number of the vertex. So since it goes right through 4, 0, then this is just 4. X equals 4 is a vertical line. The good thing about all parabolas that are right side up or upside down is their domain. It never stops going to the left, never stops going to the right. So the domain is literally all real numbers. And the way we write that in algebra is with interval notation. You put a parenthesis, a negative, click the infinity button, comma, then another infinity, and then a parenthesis. So from negative infinity to positive infinity is another way to say all real numbers. And every parabola that's right side up or upside down, that's the domain of all of them. Now the range is not everything. The graph goes up forever, but it doesn't go down forever. The lowest it gets is the vertex, the coordinate 4, 0. But the range is about y values. So if you get to the vertex of 4, 0, the 0 is the y value there. And it hits it exactly. It actually touches 0 right there. So instead of a parenthesis, you put a bracket for the 0, infinity, because it goes up forever. And infinities always get a parenthesis. And then there's another concept called increasing and decreasing. Imagine if you were traveling on this blue curve as if it was like a roller coaster. If you travel left to right, and that's the key thing, is to go left to right, the graph goes down left to right first, hits the vertex, then it goes up after that. So the domain for which the function is increasing, it's increasing when it's going up left to right. And it's all about the domain, not the range, just the x value. So starting at an x value of 4 and then going forever to the right, that's when the graph's increasing. And in increasing and decreasing, we also always put a parenthesis just like with infinities, because you're not really increasing exactly at 4. You have to be moving to be increasing. So it's never including the 4. Starting after 4 and going all the way to infinity, the graph just keeps going up and up and up forever. But it decreases the rest of the time from negative infinity until we get to 4. That's when it's decreasing. So parenthesis, negative infinity, 4, and always a parenthesis for increasing and decreasing, even on the numbers. So those two problems are the only two on the test, 2 and 3 in the homework of 3.1. The rest of the homework you can complete to get a good grade, and it will also help you learn more. But if you know those two, you'll do pretty well in the test for this section, 2 and 3. So now let's go to section 3.2. The first problem on the test is like number 3, question 3 of 3.2 homework. There's a process called synthetic division that helps us do stuff later in this chapter. So, to learn synthetic division, if you take the function, in the numerator they have a 3x to the 5th minus 4x to the 3rd plus 5x squared minus 7x plus 6 divided by x minus 2. So the x minus 2 is the polynomial that we're dividing into the big polynomial in the numerator. X minus 2, this is what's called a factor. When you have x plus something or x minus something, that's a possible factor of the function. To do synthetic division, you need its corresponding 0. And to get the 0, you literally just set it equal to 0. If x minus 2 equals 0, if you add 2, x would equal 2. This x equals 2 is in a 0 format, Zeros are written that way, x equals 2. But what a 0 really means is that this would be a solution to the top equation. If I were to plug 0 into the top part, that I would get 0 for. If I were to plug 2 in, since x possibly equals 2, if I were to plug 2 in for all the x's, would the whole function equal 0 or not? And in synthetic division, we don't always care if it equals 0 or not, but we need to use the 0, not the factor, in order to do synthetic division. So we're not going to use minus 2, we're going to use plus 2, positive 2. So you take the positive 2, and you put it in a half of a box. They call that the house. And then you just take the numbers on the polynomial, 3, -4, 5, -7, and 6. Although you do need to make sure that you have the exponents in decreasing order, and you can't skip any. So we have a 5 exponent, we have a 3, we have a 2, we have a 1, and we have a none, but we don't have a 4. So we have to include something for the 4, we can't just skip it. So I'm going to put a 3 for the x to the 5th, and you don't need the x to the 5th, you just write the 3 right next to the house. Then since there was no x to the 4th, we put a 0 for that. Then there was a -4 in front of the x to the 3rd, so that comes next. Then there was a 5, then a -7, and then a 6. So you're just writing all the numbers. The nice thing about synthetic division is you don't have to worry about the variables. Leave a little space below them and draw a horizontal line across all your numbers. Synthetic division always starts by bringing the first number down. Bring down a 3 in this case, since there's a 3 first. Most people, once they try this a few times, they find it's not so bad. All you're doing is multiplying and adding repeatedly. So you do the number you have here at the bottom, 3, times the number in the house. 3 times 2 is 6, and then you place it in the next column. Now you add going downward. 0 plus 6 is 6, and you just repeat the process till you've gone all the way across. So now I have a 6 at the bottom. 6 times the number in the house, 2, is 12. That goes below the next column. Now you add going down. -4 plus 12 is 8. 8 times 2 is 16. 16 plus 5 is 21. 21 times 2 is 42. It's either -7 plus 42, or you can think of it as 42 minus 7. That's 35. 35 times 2 is 70. 70 plus 6 is 76. The last number is a remainder if there is one. If the remainder is 0, then this x equals 2 truly is a 0 of the function, and x minus 2 truly is a factor of it. The fact that we did not get 0 for the remainder means that those really aren't zeros and factors of this function. But this is a good way that we do a lot of stuff in Chapter 3 later, where we're checking if something is a 0 or a factor. This is a good way to do it. If you just do synthetic division, see if the remainder is 0 or not. And whether it is or not, you can write the answer to this. This is really a division problem. You're dividing two polynomials. The answer are all these numbers you have at the bottom. And you just start by doing one less exponent than the original one. This was x to the 5th. It really got divided by an x to the 1st. 5 minus 1 is 4, so we're going to get a 4. X to the 4th will be our first exponent. So you take the 3 from your answer and you go 3x to the 4th. Then there's a 6, so plus 6x to the 3rd. Plus 8x to the 2nd. Plus 21x to the 1st. Plus 35, literally x to the 0, well, we don't write that. And then the 76 when there's a remainder. If there's no remainder, you're done. If there is one, it might be positive or negative. Here it's a positive 76. So you put plus or minus depending if it's positive or negative. Draw a fraction line. The 76 goes in the numerator. And the denominator is the original factor, the exact same thing that was in the bottom of the problem, x minus 2. Not x equals 2, but x minus 2. So we use the 0 in the synthetic division, but we use the factor in the answer if there's a remainder. So it's still over x minus 2. In other words, that last part didn't divide evenly by x minus 2 like the rest of it did. So this is your whole answer then. So come over here in the box, type in what you have. 3x raised to the 4th power plus 6x to the 3rd plus 8x squared plus 21x plus 35 plus the fraction 76 over x minus 2. And that is correct. So that's the process of synthetic division. It's very much like long division. This could be done with long division too, but it goes quicker when you don't have to worry about the variables. So that helps a lot, especially when we're going to be doing that more often in the rest of chapter 3. So that was problem 3. If you jump ahead to problem number 9 of the homework of section 3.2, there's a test question like this. Use the remainder theorem and synthetic division to find f of k for the given value of k. So here's what's happening. You can do this one of two ways. We have a function given to us of negative x to the 3rd minus 6x squared minus 9x minus 1. And then k possibly equals negative 4. So what that's saying is that the reason they use k is that negative 4 is a possible 0 of this function. We don't know if it is yet, so we're just calling it k. If we called it x, then that would already imply that it is a 0, and we don't know if it is. There's two ways to check if it's a 0. One is what we just did, synthetic division. If I do synthetic division with this number and the remainder is 0, then yes, this is a 0 of it, and then I'll have the answer to this problem actually. Or you can literally do what f of negative 4 means, like we did in the last chapter. F of negative 4 means plug in negative 4 everywhere there's an x. So if I do negative 4, negative, and then negative 4 to the 3rd power, minus 6 times negative 4 squared, minus 9 times negative 4 minus 1. So I've plugged in a negative 4 everywhere there was an x. There's still a negative in the front. Then I plugged in the negative 4 for the x to the 3rd, the negative 6, negative 4 to the 2nd, minus 9 times negative 4 minus 1. And if you have a graphing calculator, this can be calculated really quickly. In a graphing calculator, I can just type this all in at once. So I'm going to type in negative, I don't know if you can see that, parenthesis negative 4, parenthesis raised to the 3rd power. That's very good. There's some light. Okay. Negative, parenthesis negative 4 raised to the 3rd power. Then keep going with minus 6 parenthesis negative 4 parenthesis squared minus 9 parenthesis negative 4 parenthesis minus 1. So I literally typed the whole thing all at once. Negative parenthesis negative 4 to the 3rd minus 6 times negative 4 squared minus 9 times negative 4 minus 1. If I press enter, it says the answer is 3. That's what we were doing in chapter 2, evaluating functions at given x values. So the fact that that's a 3, f of negative 4 equals 3. This is one way to answer this question. F of negative 4 equals 3. But what's really important is that if I were to do synthetic division with negative 4, and we'll go ahead and do that just so you see one more example of it, use negative 4, and that is a possible 0, so I put the negative 4 in the house, not positive 4. There's a negative 1 x to the 3rd, a negative 6x to the 2nd, a negative 9x to the 1st, and a negative 1. So there's nothing out of order, nothing skipped. 3, 2, 1, and 0 for the exponents. Bring down the negative 1. Negative 1 times negative 4 is positive 4. Negative 6 plus 4 is negative 2. Negative 2 times negative 4 is 8. Negative 9 plus 8 is negative 1. Negative 1 times negative 4 is positive 4. And here it is. Negative 1 plus 4 is 3. That would be the remainder. And the two important things is one, that it's not 0. The remainder needs to be 0 if you're hoping that negative 4 is truly a 0 of this function. So we just showed that negative 4 is not a 0 of this function because we didn't get a remainder of 0. But the second important thing is that if you do synthetic division with a possible 0, the remainder value is always exactly the same as just doing f of negative 4. When I did f of negative 4, like we did in chapter 2, plugged in negative 4 for all the x's, the answer always matches the remainder of synthetic division. So when they say use the remainder theorem and synthetic division, it really could have said or, because they both always give you the same exact answer. If you don't get the same answer both ways, you're doing something wrong. And later in this chapter, we're going to be searching for all the zeros. So this is a quick way. A lot of it's guess and check, where you think maybe negative 4 is a 0 for some reason. So you can choose which method you like better. You can do synthetic division with it, or you can just plug it into the function, see if you get 0 or not. If you do, then you found one of the zeros, and then you'll keep looking for the other ones. If it's not 0, then you throw that one out, and you know that one isn't, and then you keep looking for the others. So there's only 2 questions on the test over section 3.2. And they are numbers 3 and number 9. Try those 2 problems as you're preparing for the test. Okay, moving on to section 3.3. This section has 4 problems on the test. The first one's like question 1. Okay, so here's where we can put into play what we just learned. They give me a long polynomial, and then it says, is x plus 5 really a factor of it? Is x plus 5 a factor of this longer polynomial, yes or no? So I got 2 choices. X plus 5 is the factor form, regardless of whether I'm going to use synthetic division or the remainder theorem. I'm going to find the 0 form of this. If x plus 5 is the factor, then x equals negative 5. It just switches because you would set it equal to 0. If it's going to work, then the 0 would be negative 5. So I can either do negative 5 in synthetic division, or I can just do f of negative 5. And in a case of yes or no, probably f of negative 5 is less work. So the original function was x to the third, so we'll do a negative 5 to the third, plus 6x squared, plus 6 times negative 5 squared, plus 3x, so 3 times negative 5, and minus 10. Here's f of negative 5. Negative 5 to the third, plus 6, negative 5 to the second, plus 3, negative 5, minus 10. I'll just type that all right into the calculator. Always put parentheses around negatives too. Parenthesis, negative 5, parenthesis, raised to the third, plus 6, parenthesis, negative 5, parenthesis, squared, plus 3, parenthesis, negative 5, parenthesis, minus 10. Get the light on here. Let me do that again. Negative 5 to the third, plus 6 times negative 5 squared, plus 3 times negative 5, minus 10. Okay, so there it is. Negative 5 raised to the third, plus 6 times negative 5 squared, plus 3 times negative 5, minus 10, and voila, 0. So if I were to do synthetic division, I would also get 0 for the remainder. So yes, this truly is a factor of this problem, and x equals negative 5 is truly a 0 of it. And in the next section, I believe, 3, 4, I think it's either 3, 3 or 3, 4, where you actually look for all the zeros. So this is a process that you're learning kind of section by section. This is what we're going to do. X to the third, it turns out the highest exponent tells you the maximum number of zeros it might have, or factors. And we're going to do some guessing and checking. So for some reason we thought x plus 5 might be a factor. X equals -5 would be the corresponding zero. This is one way to check it. Was it? Yes. Now we got one of them. One down, maybe 2 more to go. That's coming later though. This is just yes or no. So good job. Same thing here. Oh no, we're not doing number 2. So see in the homework you can do multiples of these so you get the hang of it. But there's one problem in the test like 1. I'm going to next jump to number 4. The next question's like 4. Okay, now it says factor this cubic function into linear factors given that -6 is a zero of it. So this is kind of like the first step's been done for you already. They already did the synthetic division or the f of -6, and they found out that the remainder was 0 or that f of -6 equals 0. So therefore -6 is definitely a zero of this function. But because it's 2x to the third, there might be 2 more answers. So once you find one of the zeros, the hardest part to the longest problems is finding the first zero. That can take a while sometimes. So it helps if they tell you what one of them are, like in this problem. -6 is definitely a zero. So even though I could do f of -6, all that's going to tell me is that it's a zero. If I use synthetic division with this known zero of -6, on the original problem, 2x to the third plus 3x squared minus 45x and plus 54. So I'm setting up synthetic division. The exponents were in order and nothing was skipped. We already know, because the problem told us, that -6 is a zero of this function. So we better be getting 0 for a remainder or something's definitely wrong. But after we finish this, you'll see that we can find the other zeros much faster than guessing and checking. So bring down the 2. 2 times -6 is -12. 3 plus -12 is -9. You multiply up and add downward. -9 times -6 is positive 54. 54 minus 45 is 9. 9 times -6 is -54, and as I knew would happen, the remainder is 0. It has to be. If I don't get 0 there, something's definitely wrong, because they told me it was a 0. The original problem had x to the third in it, so our first number of 2 is going to be 2x squared minus 9x plus 9, and there's no remainder. So what this is telling me is the original problem of f of x equals 2x to the third plus 3x squared minus 45x plus 54. That's a problem that's hard to factor all together like that. But I now just learned that one of the factors is this, 2x squared minus 9x plus 9. 2x squared minus 9x plus 9. And since -6 was a zero of it, then if you switch that, if you have a 0, you can go back to the factor just by switching the sign. So if x equals -6 is a 0, then x plus 6 would be a factor. And usually we put the smaller factors in the front. So we've just factored this big thing into x plus 6 times this trinomial. And because the trinomial is x squared, we spent all chapter 1 learning how to solve quadratics. So that could be simplified further with the quadratic formula, with completing the square, or maybe even just factoring. I would try factoring first. They won't all factor, but maybe this one will. So that's the advantage, is after you do synthetic division, if you can get it down to a square, then you might be able to get the other 2 answers at once. The only way to get 2x squared is 2x times 1x. 9 could be 1 and 9, or 3 and 3. Let's see if 9 and 1, we got to try to multiply to 9 but add up to a negative 9 in the middle. 3 and 3, see it's going to be 3 and 3. And they're going to both be negative because I need negative 3 times negative 3 to give me this positive 9. And then if I do the inside and the outside in reverse FOIL, 2x times negative 3 is negative 6x. Negative 3 times x is negative 3x. So if you have a negative 6x and a negative 3x, yes, that adds up to negative 9x. So if I was given this quadratic to factor back in chapter 1, it would factor into 2x minus 3 and x minus 3 just using factoring techniques. Plus I already have the x plus 6 factor. So there's 3 factors to this problem because the highest exponent was a 3. These are the 3, and this is the answer to this problem. We could also get zeros by setting each of these equal to 0. There would be 3 zeros to this problem, negative 6, which we already knew because they told us that one. We could get positive 3 also. And then if you set 2x minus 3 equal to 0 and solve it, you'll see that it turns out to be 3 halves. So whenever there's 3 different factors, then you'll have 3 different zeros to this problem. And the highest exponent 3 tells you the maximum number. Sometimes you don't get all 3 because sometimes they repeat. And we even have some where we get imaginary answers because sometimes something like this doesn't factor so nicely. Here we were lucky that it factored out. That doesn't always work, but... So here it says factor completely. I'm going to put all 3 of those parentheses. There's the x plus 6. And the order doesn't even matter either. 2x minus 3. And the third one is x minus 3. Check answer, and it is correct. The third problem here is like number 7. Okay, we were told in that last problem that x equals negative 6 was a 0. That's not always so convenient. That's actually hard. So we were kind of lucky that they told us that. Most of the time, you have to find all the zeros yourself, and that's the hardest problem in the chapter. Is they just give you a polynomial and they say find all the zeros. Well, it's not just blindly guessing negative 6 and things like that. There's actually a couple of techniques you can put together that'll help you get to good things to guess. And one is this thing where it says list all possible rational zeros. So from the original function, x to the third plus 8x squared plus 5x minus 14. Okay, so the last number, when these are in order, the last number here is negative 14. That's called p, and the negative isn't so important because we're going to be doing plus and minus on everything anyway. And the front coefficient, which here is blank, so it's a 1, that's called q. So we got a p of 14, a q of 1. If we list all the factors of each of those numbers, the factors of 14, things you can divide into 14 are 1, 2, 7, and 14. They're the only numbers that divide evenly into 14. It's nice when q is a 1 because the only thing that divides into 1 is 1. So we make a list of possible rational zeros is all the p divided by q combinations. And every single one you put plus or minus on it. And whenever q is a 1, it turns out the list is all the p's. Because you're literally just doing 1 divided by 1, 2 divided by 1, 7 divided by 1, and 14 divided by 1. Everything divided by 1 is itself. So we really just get the p list here. 1, plus and minus 1, plus and minus 2, plus and minus 7, and plus and minus 14. So on the original problem, when it was x to the third, there might be 3 zeros to this function. And some of them may be repeats, some of them may be imaginary numbers, but in cases where we get 3 real zeros like we did on the last problem, say they're all real numbers, if they are, they're going to come from this list only. the only possible rational answers we can get have to be plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. This is how they knew in that last problem that -6 was a 0. You can get a narrow list sometimes like this. There's only 8 numbers to check here. So I could either do synthetic division with them, I could do f of 1, f of 2, f of 7, f of 14, f of -1, f of -2, f of -7, f of -14. At worst case, I'd have to check 8 answers to see if any of these are zeros. And if not every answer is a rational answer, but the ones that are rational, which happen the most, the good thing is they only come from this list. So this is all you have to check. And you don't have to check 3 or 4 or 5 or 6 or 8 or 9. It's a waste of time to check numbers that are not on this list. So the guess and check process can take a while sometimes, but at least it's not just a blind search through an infinite amount of numbers. Here we only have 8 possible numbers that could be the answer. So this is a multiple choice, and they have A. A is usually the tricky answer. They have all the 4 numbers in A, but they don't have the plus or minuses. And C's missing 14. B's just got a few of the numbers, but it's D, where it's plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. So they ask questions and homeworks and tests just about this part, but this is like the first step of the whole process when we get to the problems where we're finding all the zeros. Okay, so then, now that we know those ones are, we can check them to see which ones are rational zeros and which ones are not. And the process I usually do is I start with the easiest one, positive 1. I'm just going to find f of 1. So this is like the last section. If I do f of 1 and the answer is 0, then yes, 1 is a 0. If it's anything but 0, then it's not a 0. So 1 to the 3rd power plus 8 times 1 squared plus 5 times 1 minus 14. And you can use a calculator if that helps. Here with the 1s, it's probably quicker without one. 1 to the 3rd power is 1. 8 times 1 squared is 8. 5 times 1 is 5. And then there's a negative 14. And 1 plus 8 plus 5 is 14. Minus 14, yes, it's 0. So I immediately know, even though I might have had to check 8 numbers, I got lucky. The first one I chose to guess actually worked. X equals 1 is one of my 3 possible zeros. And yes, I could keep going down the list. I could do f of 2 next. I could do f of 7, 14, negative 1, negative 2, negative 7, negative 14. But we might be wasting time doing that. This might turn out to be the only answer. So a quick way to tell is I would do synthetic division next with this known 0, just exactly like the last problem. We are now at the point that the last problem was where they told us negative 6 was a 0. They just told it to us there. Here we had to do all this work to find it. But if we do synthetic division on the original problem with this known 0, we have to get 0 for a remainder for sure. But what the nice thing is it'll drop us from an x to the 3rd to an x to the 2nd problem. So bring down the 1. 1 times 1 is 1. 8 plus 1 is 9. 9 times 1 is 9. 9 plus 5 is 14, and yes, 14 times 1 is 14, so that way we get no remainder. We have to get no remainder here. The original problem was x to the 3rd, so that means we're down to x to the 2nd. And with a 1, that makes it nice too. 1x to the 2nd plus 9x plus 14. This is the other factor, and if I set it equal to 0, and factor it, we can find the other 2 zeros, possibly. And this is easier to factor than the other problem. The only way to get x squared is x times x. If both of these are positive, then both of your answers are positive. We need 2 numbers that multiply to 14 and add up to 9. Well, that's 7 and 2. So these are the factors. The zeros would be x equals negative 7 and x equals negative 2. And notice both negative 7 and negative 2 were in my list. They have to be. But I could have found them also with just doing what I did with 1. If I did f of 1 to figure out that was a 0. So it would have worked to do f of -2 and f of -7. The problem is it doesn't always work. If there's 3 answers, you don't always find them from this list. There could be imaginary answers that we would never get from this list. Or maybe repeated answers, and you could be, there's some problems where you find 1 in the list, and if you check all the rest, none of the rest work. So that's why I wouldn't suggest checking them all. You could if you want, but you're not always going to get all the answers that way. And look how long it would have taken. You probably would have done 2 second, 7 third, 14 fourth. Then you probably would have went to -1 next, then -2, then -7. So you would have had like 7 calculations just to find the 3 answers. Here I was able to get the other 2 answers together. So there are 3 zeros to this problem. There's the -1 that we found, or there's the +1 we found first. And then synthetic division with that led me to the other 2 answers together, -7 and -2. So this answer is A. It's still part of the same problem. 1, -2, and -7 are the 3 rational zeros. Because there can be irrational zeros and there can be imaginary zeros too. So this only tells us about the rational ones. And the last part's easy, because if you have +1 as a 0, then you need an x minus 1 as a factor. If you have a -2 0, you should have an x plus 2 somewhere. And likewise with -7, there should be an x plus 7. So this one's D, x minus 1, x plus 2, and x plus 7. Those are the 3 factors that match up with the 3 zeros where all the signs are opposite. Check answer, and it's correct. The last problem from this section is like number 9. Okay, here's another thing, that if we are able to find zeros and factors, we might be able to rewrite a function or a polynomial in its factored form, kind of like that last answer I had where I had the 3 factors in parentheses. Now, once you have your factors in parentheses, you can see the zeros from them. Like x minus 5, that has a 0 of x equals 5. I've already mentioned how even if you're able to find rational zeros, sometimes they're repeated answers. And this is a way to see that. If you have x minus 5 to the 4th power, it's going to turn out that x equals 5 is a 0, but it's actually going to happen 4 times because of this 4 exponent. So this is a concept called multiplicity. Multiplicity is when answers repeat. And if you have a polynomial in factored form, as opposed to the long polynomial that we had on the last problem where it was x to the 3rd plus 9x squared plus 5x minus 14. When it's in this form, you can't see the factors of the zeros. It takes a while to find them all. But when it's in this form, you can see all the factors and all the zeros right away. And if they're factored and with exponents, then they have a multiplicity larger than 1. So there is an x equals 5, 0, and it has a multiplicity of 4, which means it literally happens 4 times. So in choice A, there's that part at least. 5 is a 0, and it has a multiplicity of 4. That means that answer's happening 4 times. B doesn't have that, so that's out. C has it, and D has it. So the only one I can eliminate so far is B. Now the next factor is 5x plus 1. If you set that equal to 0 and solve for x, you would subtract 1 and divide by 5. The next 0 would be x equals -1/5. And since it has no exponent, there's really a blank 1 here. Then it's a multiplicity of 1, which they really don't mention. So yes, -1/5 is another 0. A multiplicity of 1, that's just understood. They don't put that. So it could be A, could be C, and it could be D. That didn't help because those two, that's there in all 3 answers. Okay, so the last factor is x squared minus 16. But notice it's x squared. So we could actually factor that a little bit better. X squared minus 16, this is a type of factoring called difference of squares. One is x plus 4 and the other one's x minus 4. So there's two more zeros coming from this, -4 and +4, and they're each happening once, so they each have a multiplicity of 1. So A is wrong because it says +4 has a multiplicity of 2. We didn't get +4 for both of them. We got one +4 and one -4. So that's like this here, +4 and -4. Although D has it too. But D's wrong because they have an extra -7 that we never had a -7. Don't let this front 7 trick you into thinking that -7 is a 0. This is not a factor, this is just a constant. Factors and zeros have to have x with them. This 7 does not have an x. So if you set this whole thing equal to 0, you could literally divide by 7 and it would go away. So a front 7 or any constant in front does not lead to any zeros. So that's the tricky answer, D, that some people think the -7 is also a 0. It's not. This answer is C. 5 is a 0 and has a multiplicity of 4. -1/5, 4, and -4 are 3 more zeros. They all happened once, so they just have a multiplicity of 1. So the answer is C. Section 3.3 has 4 problems on the test. It's like 1, 4, 7, and 9 in the homework. Try those 4 problems. Okay, we got 2 sections left. The 3.4 also has 4 problems. The first one is like number 2. Okay, this is what another thing we're looking for is zeros can be seen in a graph. They're called zeros because it's when the y equals 0. This spot right here on the graph, when the graph crosses the x-axis, that's what a 0 is when you cross or touch the x-axis. Because the coordinate right here would be 2, 0. The y is 0. That's the whole goal on these problems, is to figure out what makes y equal 0. So a graph like this, it's curved, it could end up crossing the x-axis more than once, but this one literally only crosses at one time. So you can see the real zeros on a graph, how many times it crosses or touches the x-axis. This is only 1. Now that was kind of simple. Maybe if I go back to number 2, here's the same problem. If I hit similar exercise, that's one nice thing with the homework is you can do problems over and over again. I guess not. I was thinking maybe it would give me one where it crosses more than once, but sometimes you get these curves, they go up, past the x-axis, they come back down, and then they go back up again. You might get more than one, but this, for some reason, this is always coming out to 1. Here's a good example. We're not going to do this problem, but this graph right here, this D graph, this crosses the x-axis once, twice, 3 times. So this would have 3 real zeros. And it turns out if you cross through an x-axis, you have a odd multiplicity, like 1 or 3. If you do this C graph here, it's coming down, it crosses through the x-axis, then it comes up and it just touches it and goes right back the same way it came from. Then it crosses through, crosses through. So there's 4 different zeros on this graph. 4 different times it touches or crosses the x-axis. This would have 4 zeros. But the one where it kind of bounces off of it, that would have an even multiplicity like 2. It would be a repeated answer. So that's why that last problem, it was important to see the exponents of the factors, because the multiplicity will tell you what's happening on the x-intercepts. Are they crossing through them or are they bouncing off of them? You don't need to worry about number 3 for the test, though. I just wanted to show you another graph. So here's number 4. When we're given this long polynomial, x to the 4th, this is hard to find all the zeros for it. But if we have a graph to look at, then it becomes real easy. The graph comes down and it bounces off -3. So -3 is a 0, and because it bounces off of it, it has to have at least a multiplicity of 2. Whenever you bounce off the x-axis, you have an even multiplicity, 2, 4, 6, or 8, or something like that. So usually we just assume the simplest one it could be of 2. Then it goes up, comes back down, and it crosses right through 0. But it crosses through it, it doesn't bounce off of it. So that's a multiplicity of 1 or 3 or 5, probably 1 here. and then it crosses through positive 3. So I would say there's 3 zeros, because it touches or crosses the x-axis 3 times. It crosses or bounces off negative 3, crosses through 0, and crosses through 3. There's 1 bounce and 2 crosses. Bounce means you have to have at least a multiplicity of 2, but some even number. If you cross, you probably are 1s, but it could be 3 or 5 also. But the original problem was x to the 4th, so the most there can be is 4 zeros, 4 solutions. We're only getting 3 because 1's a repeated 1. The negative 3 is happening twice. That's what the multiplicity tells you. A multiplicity of 2 tells you the answer is happening twice. This answer is happening twice, and these 2 are happening once. There's your 4 answers. There really are 4 answers. 3, 0, and negative 3 twice. So if we change these zeros to factors, you would get x plus 3 for the x equals negative 3. X equals 0 would literally be x minus 0, but that could just be x. X minus 0 is the same thing as x. And then x equals 3 can be x minus 3. Those are the factors. The 0 had a multiplicity of 1, the 3 had a multiplicity of 1, but the negative 3, 0, or the x plus 3 factor, that had a multiplicity of 2, so the exponent there would be a 2. And this is the answer they're looking for, is what is the factored form of the polynomial? This is really hard to do without the graph, but with the graph it becomes easy. X is one factor, parenthesis, x plus 3, parenthesis squared, and x minus 3 is the last one. Okay, here's a 3x to the 6th power problem. So because this is just x to the 6th, 6 tells me that it's an even exponent, so therefore it's got a multiplicity. Whoops, we lost that. Where did it go? Oh, wait, we might not even be doing that problem actually. That was number 4. Okay, let's go to 8 next. Eight is the third problem here. Okay, so yeah, forget what I was just saying because that one's not on the test. Okay, another thing that helps when you're doing these graphs is all these polynomial graphs, when you go way to the right or way to the left, the graph just shoots way up or goes way down. That's all that ever happens. So you get this concept called end behavior. Describe the end behavior. And it'll tell you what's happening way at the beginning and the end of the graph. Are they going in opposite directions? Are they going in the same direction? There's literally these 4 possibilities on every problem. And it can be told from, if you look at the polynomial and find the highest exponent, that's the whole key thing, the highest exponent, the other stuff doesn't matter, 2x to the 5th tells me everything about the end behavior. The 5 is an odd exponent, and the highest exponent in this form is the degree of a polynomial. This is an odd degree polynomial, and it's got a positive 2 in the front. This is called a leading coefficient. A leading coefficient is the number attached to the highest exponent. And if you get an odd degree, then the end behavior is one of the ones where they're going in opposite directions, A or B. If you get an even degree, they're either both going down or both going up. So since our degree is odd, 5, we have one of each. And then when it's a positive leading coefficient, the answer is going to be A. And here's how I remember that. I remember from chapter 2, when you learned all the parent functions. X squared is the most basic even function. There's an even exponent, even degree, and we hopefully know what that graph looks like. It's a U-shaped parabola. This is your end behavior when you just look at the end and the beginning of the graph. way off to the left, way off to the right. This graph's going to shoot up forever and shoot up forever. So in an even power degree, and there's clearly a positive 1 right here, when it's positive and even, both arrows go up on the ends. So if there's a negative in front for the leading coefficient, then you do the opposite and they're both down. The most basic odd function among all the parent functions is x to the third. This is odd, and the parent functions have a positive 1 in front. So this is a positive odd, just like the problem we have. If you know the shape of this parent function, it curves up on this side, but curves down on that side. So starting down low and ending up high, that's what odd positives do. That's the kind we have. It doesn't matter what odd number it is. The degree is 5, that's odd, and the leading coefficient's 2, that's positive. All positive odds have this end behavior right here. If it was a negative odd, then you would just do the opposite case, where it starts up high and ends down low. Then there's one more of these on number 10. And this is an easy one to trick somebody on a test. Look at the 4 plus 5x minus 2x squared minus 3x to the 10th. You got to get to the highest exponent. Negative 3x to the 10th. That's all I want to look at. Negative 3x to the 10th. The 10 is an even degree. But it's a negative 3 in the leading coefficient. And see, that's kind of a word that misleads people. Leading coefficient. So people look at the problem and they go, well, the 4 is leading the pack. So they think this is the leading coefficient. That's not true. The leading coefficient, it's kind of misnamed to call it leading because sometimes it's in the rear. The leading coefficient is the number attached to the highest exponent. So don't let that trick you on a test. We have an even degree. That means they're both going in the same direction, but it's a negative leading coefficient. Normally, evens look like parabolas like this one when the leading coefficient is positive. So if it's negative, you pick the one that's opposite down here on C. This one's C because of the negative leading coefficient. Okay, so the 4 problems from section 3.4 are right there, 2, 4, 8, and 10. Okay, last thing for this test is section 3.5. This one's got 6 questions because some of these are shorter than others. The first one's like number 1. This is what are called rational functions. The most basic rational function, parent function, I guess you could call it, is f of x. We've seen x squared, we've seen x to the third. There's one that goes 1 over x. That's called the reciprocal function. And the graph looks like this. It starts up here around 0 and it curves until it gets close to the y-axis and it just shoots down forever. And then it picks back up again up here at the top and comes down like this. But the graph never touches or crosses the x or y axis. These are kind of like imaginary boundaries that we never get close to. Or we get close to them, I mean, but we never touch them. So this happens with rational functions. As soon as you have a fraction with variables in the denominator, the problem is you can never divide by 0 in math. So if I plug a 0 in for x, I get 1 divided by 0. That's undefined. So that you can't put 0 in for x. If x is 0, the graph literally doesn't exist because it would be undefined. So that's the concept they're getting at on this first problem. They're saying if your domain is negative infinity to negative 1, union or negative 1 to infinity, this literally is every single number except for number 1. This is a way to say all real numbers except negative 1. Because we're putting a curved parenthesis around the negative 1 on both sides. So this includes everything but negative 1. So what that's going to do to the graph, see all these graphs look alike with these curves going kind of opposite of each other. But what this is telling me is that the graph doesn't exist at negative 1. There's that imaginary vertical boundary at negative 1. So if I blow up this graph maybe See how this graph crosses the y-axis, so that's fine. 0 was the imaginary boundary last problem, but here it's over to the left of that a little bit. So it's hard to tell with this going by 2's, I guess. There's -10, -8, 6, 4, -2, -1's right here. So this could be the imaginary boundary of -1. It's certainly not getting to -1 at all on either side of these two curves. Whereas B is definitely wrong, because at -1 I can see the graph went right through an x of -1. The imaginary boundary here is over on the right side. C is wrong because it's shifted way to the right. The imaginary boundary is way over here. And -1 is definitely something we're passing through. And same thing with D. This one's probably +1, and -1 is definitely an answer. So the answer to number 1 is A, because it's the only one where you cannot touch -1 at all. -1 is not in my domain, and my graph never crosses or touches anywhere where -1 would be. Same deal. Oh no, this one's not on the test. Yeah, it is. Okay, there's another one here. Number 2 is also on there, 1 and 2. So now we're saying everything but 3. We want to go -infinity to 3, and then 3 to infinity. So in other words, everything but 3. So we need a graph where if you draw a vertical line at x equals 3 approximately, make sure the graph never goes through that spot. Well, it does here. This spot, this curve goes right through 3. This one looks like 3 could be the imaginary boundary. C is definitely wrong. 3 is right there. And D, it definitely goes through 3. So this is B. In graph B, there would be an imaginary vertical line at -3. If you draw a vertical line through 3 of the x-axis, the graph would never touch that line. This graph, this right graph, is curving, and it's kind of like there's an invisible wall there. As it's traveling this way, as it gets close to 3, it has nowhere to go but up, because it can't pass through 3. It can't just keep going this way. It gets close to 3 and it just gets repelled away like a magnet. Or coming from left to right on this curve, once it gets, you would think it would just keep going right through 3 like most graphs do, but it doesn't. There's like an imaginary force field there or something, like in Star Wars. And it just bounces right off of it. You can't pass through. That's an imaginary boundary you can't pass through. So this is B. Or did I misread it somehow? Oh, okay, yeah, it was. I didn't read it closely enough. What switched on number 2 was it said the range, not the domain. So not only can there be a vertical imaginary boundary, there can be a horizontal one. The range is about the y's. So we want where the y3 going this way, you never cross it or touch it. So B, you actually do through a horizontal 3. Here's the one right here, C. If I go up to 3 on the y-axis right there, 1.5 on, because these are going by 2's, 2, 3, draw it out this way, you're going to get closer and closer to that but never touch it. And then same thing on this side, closer and closer to it, never touch it. There's this imaginary boundary horizontally. So this one was actually C, so watch out for 1 and 2. 1 says identify the graph with a domain. Domain is vertical, because that's x. 2 says the range, which is the y, that's horizontal. The third question is like number 6. Okay, these imaginary boundaries have a funny name that most people have never heard of before they get to this class. They're called asymptotes. Asymptote is an imaginary boundary that you usually don't cross or touch. And that's what this section is mostly about, are the asymptotes. When you're given a rational function, a function with a fraction in it, it really comes down to the denominator. Could the denominator equal 0? Here it could. If you have x minus 3 over x plus 4, we take the denominator, because that's the only thing we worry about is what makes the denominator equal 0. It's okay if the numerator is 0, but if the bottom is 0, the answer is undefined. And it's kind of like what we were doing before with factors and zeros. It's kind of like the 0 of the denominator. X equals -4. This is an issue for us because we can't plug it in the original problem without getting an undefined answer. So as long as your fraction is as reduced as possible, which isn't always the case, but as long as it's as reduced as possible, anything that makes the bottom 0 is a vertical asymptote. So I just call this VA for short, vertical asymptote. So at x equals -4, there would be a vertical imaginary boundary, just from this information alone. And then we're not going to graph these at this point, but the curve would come something like this, and then there'd be another one up here like this. So from this equation, I can tell there's an imaginary boundary vertically at -4, because we got x equals -4 makes the bottom equal 0. And that's the answer C. There's a vertical asymptote at x equals -4. Because it makes the bottom equal 0. Okay, the fourth problem is like number 8. Okay, so then instead of giving me multiple choice, they just say, what is the equation of the vertical asymptote? Vertical asymptotes are always vertical lines, so it's always x equals some number. And the number's mostly easy to find. It's whatever number makes the bottom equal 0. So if you have to just set the denominator equal to 0. X minus 3 equals 0. You would add 3 to the other side, and you would literally get, it's like going from a factor to a 0. X minus 3 is like a factor, so x equals 3 is the 0. And in these graphs, we cannot have 0 in the bottom. That'll cause it to be undefined. So that's the vertical asymptote. Vertical asymptote is any 0 from the denominator, and sometimes there's more than one, as long as the numerator, as long as you can't reduce the fraction anyway. Sometimes they give you a fraction that's not reduced. If you can reduce it first, then you might get something that makes the bottom 0 that doesn't count. So that's your first step in the final problems. They're gonna ask you about the vertical and horizontal asymptotes. And the vertical are the easier ones. It's just whatever makes the bottom equal 0 for the most part. Horizontal asymptote equations are horizontal lines, so they're always y equals some kind of number. They're not quite as easy to get as vertical ones. There's really 3 cases. It helps to know the degree of the numerator and the denominator. So if you have this function was 5 over x minus 3. We need to see the degree of the top and the degree of the bottom. Degree are the highest exponents. So this one has a degree of 1, x to the 1. The 5 is a constant. It's literally 5 x to the 0. We normally don't write x to the 0, but we could. So if there is no x, the degree is 0. When the bottom degree is bigger, 1 is bigger than 0. When the degree is bigger in the bottom of these rational functions, you automatically get a horizontal asymptote of y equals 0. In other words, the x-axis. Y equals 0 is a horizontal asymptote anytime the bottom's bigger. And the way I remember that is go back to the parent function. The parent function of all rational functions is 1 over x. It looks like this. That has a vertical asymptote of 0 and a horizontal asymptote of 0, because we never touched the x or the y-axis. And in that one, clearly the denominator degree is bigger. 1 is bigger than 0. So that's the case I always remember, is the parent function, oh, that's when it's y equals 0. So if you get any that are like that, where the bottom has a bigger degree, the horizontal asymptote is always y equals 0. Next case, we got 2 cases to go. Here's a rational function where the bottom does not have a bigger degree. The top is 5 minus 5x, and the bottom is 4x plus 6. Now watch out again if they're out of order. The highest exponent anywhere in the top would be the x to the 1. The highest in the bottom is also 1. The constants are zeros. So they both have a degree of 1. They're equal to each other. When they're equal to each other, the horizontal asymptote is y equals the two leading coefficients divided. But you got to be careful because some people think the leading one is the 5 because it's in the front. Again, the leading coefficient is the number attached to the highest exponent. So negative 5 over, it's literally negative 5 over 4, just what you would see in front of each of the highest exponents. And then the vertical asymptote, as always, as long as the fraction's reduced, and this one is you just take the bottom and set it equal to 0. And solve for x, this will be the vertical asymptote. Subtract 6, divide by 4, reduce it if you can, negative 3/2. So negative 3/2 is the only number that makes the bottom 0. The fraction's as reduced as possible. So negative 3/2 is the vertical asymptote, and negative 5/4 is the horizontal. So it says first, is there any vertical asymptotes? Sometimes there isn't. Sometimes there's no vertical asymptote. If the denominator can't be 0, then there is none. In fact, most graphs you've learned in your whole math career never had a vertical asymptote. You've never seen them before this section. So most don't have one. But if the bottom can be 0, then you get a vertical asymptote. So this is negative 3/2. Then they ask you about any horizontal asymptotes. Not every problem has one of those either. So this one does. It's y equals negative 5/4 because the degrees were equal, and that was the two leading coefficients divided. One last case. Oh wait, there's also a concept called an oblique asymptote, which is a diagonal one. And you don't get one of these anytime there's a horizontal. You can never have both a horizontal and an oblique or sideways asymptote. So if you answered anything for the horizontal, then this is definitely going to be none. Okay, third and final case, and this is the last problem on the test, is here's the final case. We've seen the case where the bottom had a bigger degree. We just saw the case where they had the same degrees. The last case is when the top has a bigger degree. X squared minus 5 over x plus 5. So the fraction cannot be reduced. The vertical asymptote's easier. What makes the bottom 0? Negative 5 would. So there's definitely a negative 5 vertical asymptote. It's the one number that makes the bottom 0. Okay, horizontal asymptote. Three cases again. When the bottom is bigger degree, then it's y equals 0. When they're equal degree, you divide the two leading coefficients. So this was a 2. If this was a 2 here, it would be y equals 1 divided by 1. But here the top's bigger because it's a 2, the bottom's a 1. Whenever the top is bigger for degree, then there is no horizontal asymptote. So finally, there could be an oblique asymptote. The only time they happen, though, is if the top has to have a bigger degree to have a chance to have an oblique asymptote. So it's only going to happen on these cases where there's no horizontal. So you never get both of these. It's either one or neither. And the only time it can happen is not only when the top is bigger, but the top has to be bigger by just 1. Here the top is 2, the bottom is 1, that's 1 bigger in the top. If the top was 3 and the bottom was 1, then there would also be no oblique asymptote. But here there will be one because the top has 1 degree bigger than the bottom. So to find what it is, all you have to do is divide them, either with long division or synthetic division. I would go ahead and use synthetic division because x plus 5 makes that easy. X plus 5 is a factor. So I could do negative 5 in the house as the 0 for x plus 5. And then I have a 1x squared, and there's no x to the first, and then there's a negative 5. So I'd put a 1 for the 1x squared, a 0 because there's no x, and a negative 5. Bring down the 1, 1 times negative 5 is negative 5. 0 plus negative 5 is negative 5. Negative 5 times negative 5 is 25. Now, these don't have to have a remainder of 0. They usually don't. The remainder is 20, actually. But the good thing is the remainder has no effect on an oblique asymptote. So you can really ignore that. So again, the original problem was x squared, so that means we're going to be 1 less than that. The 1 we got in the front, that's going to be 1x to the first minus 5. Or in other words, x minus 5. That's the oblique asymptote. If you divide them, whatever you get in the synthetic division other than the remainder, that's the equation of the oblique asymptote. And it's x minus 5 because it's literally a diagonal line. This is a diagonal line that has a slope of 1 and a y-intercept of negative 5. So there's 3 cases of horizontal asymptotes. When the bottom has a bigger degree, then it's y equals 0. If they're equal in degree, it's y equals whatever the leading coefficients divide out to. And if the top's bigger, there's none. In the case when the top's bigger, there may be an oblique asymptote, but only if the top's 1 bigger. Section 3.5 has these 6 questions. There's a total of 18 on the test. So that's a good review for the test. You can study this weekend, and the test is open Monday through Friday next week. Email me if you have any questions.